speak about my published paper in Fuel last year, the theoretical reaction rate model of a chemical exothermic decomposition surface from an external gas. The paper is extensive in mathematical derivation, but I have compressed it into basic ideas in this presentation. Introduction. I will present a physical model with physical parameters. It's an analytical model and not a computational one. It's not empirical either. A new concept of covolume is introduced. Kinetic theory is used to establish equation of state. Closed form expression for linear reaction rate is achieved. A simple formula for activation energy is also achieved. If we are interested in amount of generated gas, we need to look into geometry and porosity. And lastly, I will compare theoretical model with experimental data. Covolume. There are three main parts to the new covolume model. Part 1 is that when we measure over time, each point in a volume eventually contains information regarding every possible interaction. Part 2 is that the particles can be grouped together into blocks that interact equiprobably. These two parts are illustrated in the configuration space above in the figure. The colored squares are different blocks, and we see that every possible interaction between blocks is contained in the configuration space. We also see that this leads to that each colored block is represented more than once in the configuration space, which means that each particle is represented more than once also. That leads us to the third part, where we count only distinct blocks at a time, and that gives us the covolume, where each particle is only present once, and that leaves room for blank space. Joule probabilities. The difference in block volume and covolume produces two probabilities. First one is the interaction probability nu, which models mass change with block volume, because the interactions are modeled in blocks, as was shown in the previous slide. The second one is reaction probability pi, which models mass change in covolume, because the entire particle must engage in the reaction. The block density d used above is modeled as the particle density given by the Lennard-Jones potential at a given temperature. If you plug in the temperature as the potential energy in the Lennard-Jones potential, you can find a radius for the particle that corresponds to that density that we call block density. This enables us to handle the molecules as particles. There are initial values for interaction and reaction probability, which is autoignition and activation energy accordingly. This can be shown with the help of the Maxwell-Boltzmann distribution. Kinetic theory and linear reaction rate for eroding decomposition surface. To find the linear reaction rate, we begin with the energy momentum conservation for a decomposition surface. The left side of the equation is the unreacted side, and the right side is the reacted side with subscript 1. Subscript V is surface and subscript L is gas. We see that the heat of reaction is stored in the unreacted side, and when released, it's transformed into velocity. We need a third equation, an energy balance that includes activation energy UA. There are two parts to this equation. First one is that the surface reacts only at the ignition points, hence nu times surface mass. The second one is the portion of the gas that reacts is the reaction probability, hence pi times gas mass. To model an eroding surface, the linear reaction rate Vb must be added to the internal gas velocity to get the total kinetic energy of the gas that reacts. This kinetic energy must be equal to the activation energy needed to sustain the reaction, shown left in the equation. Combining these three equations above, you get the linear reaction rate Vb, which depend on the gas pressure P, unreacted density rho B, the heat of reaction UB, the interaction and reaction probability nu and pi. These equations change depending on the reaction type. If you have something else than a eroding decomposition surface, you need to redo these equations to get a new linear reaction rate. Pressure. The complexity of pressure expression comes from solving a cubic equation, but basically it's a gas density dependence. Pressure and temperature curves for HMX. Surface pressure peaks at high gas densities. Temperature remains approximately constant for low gas densities, then drops to zero for high gas densities. For comparisons, the density of HMX is 1960 kilograms per cubic meter. Activation energy. The gas pressure and temperature is dependent on activation energy UA. This is a complicated expression, however the problem can be simplified greatly by looking at near zero gas density, in other words idle gas. The energy storage or closed vessel temperature is related to the gas temperature with a factor of 2, because only half of the released gas will kick back at the surface. With this simple step, we can derive a simple expression for the activation energy, UA, which is equal to 1/4 times square root of heat of reaction UB and energy storage UC. This expression of the activation energy is valid for both exothermic and endothermic reactions when the sign of heat reaction UB is omitted. Activation energy for hydrogen. I will attempt an example of activation energy for hydrogen reacting with oxygen to form water. The energy storage for this reaction is 120 megajoules per kilogram. The heat reaction to split hydrogen and oxygen to atoms is 218 megajoules per kilogram for hydrogen and only 31.1 megajoules per kilogram for oxygen. That means that the decomposition of hydrogen determined the activation energy to form water. Plugging this into expression for activation energy from previous slide yield 80.9 kilojoules per mole. For combustion or oxidation, overall activation energy typically ranges from 64 to 83 kilojoules per mole for high temperatures, so it fits well. Geometry and porosity. If you are interested in generated gas, we need to look at geometry and porosity, where the mass fraction μb measures the fraction of reacted material. The rate of generated gas is expressed by fraction rate and is related to the linear reaction rate Vb with a geometry factor g that is surface over volume. When the volume is constant, the porosity phi is directly related to mass fraction μb with the initial values. The same applies for the gas density, directly related to mass fraction and the initial values. Gas density is important because it's the main input parameters to linear reaction rate Vb. Burn rate data for HMX. Lastly, I will show you an example of theoretical burn rate for HMX and explosive. HMX is a good example to verify the model due to the many orders of magnitude that data spans over. I have used literature data to establish physical parameters for the model of HMX, shown as below. These parameters completely defines the theoretical model for HMX, and you see the result in the figure to the right. The red and green line is theoretical model, where red is for low gas densities and green is for high gas densities that we usually don't see. For low gas densities, we have a pressure chamber that gives us data, and the theoretical model fits very well with the experimental data. For high densities, diamond anvil experiments are used that measures small grains of HMX. There is more uncertainty and spread in the data, but the theoretical model fits reasonably well to the experimental data. The burn rate for HMX ranges from millimeters per second to 180 meters per second, reaching up to 12.8 gigapascals. To summarize, the physical quantities that govern the reaction are both ignition temperature, activation energy, heat of reaction, block density, closed vessel temperature, gas temperature, surface density, and particle masses. If you can control these quantities, you can control the linear reaction rate. Conclusion. A fully physical model of linear reaction rate is established. Good agreement with experimental data. The parameters used in the model have physical origins. It's a fully theoretical model and not empirical. Simple expression for activation energy is achieved. For other reactions than decomposition surface, other equations of state must be considered. There is further work on other types